Okay, so hello everyone. Welcome and thank you for being here today. I'm going to present to you my PhD thesis plan and what I've done so far. And it revolves around self-supervision, reinforcement learning, and imitation learning for visual tactile robot manipulation. Now, before we start, I would like you to imagine that it's a sunny day, like now, here in Leoben, and you want to find your sunglasses. You're at your home. So you look around you, and you filter out all the relevant information, like the stack, the pile of clothes that you have in your bed, or the scenic view from your window, if you're lucky enough, and you spot your bag hanging from your desk chair. What your brain has already done is to seek for shapes that look like your bag to identify it. And in that way, it uses abstract representations since you cannot actually draw your bag in detail if I ask you, but you can very easily recognize that. After that, you reach for inside your bag. You create a specific trajectory to get it into your bag, and there, your finger starts to navigate around the different objects in there. They go through the soft and yielding texture of your wallet, and maybe the rigid, angular notebook that you have in there. You feel the metallic cold keys that you have, and there is familiar sense of smooth and hard case of your sunglasses. Then your thumb and finger close together to secure the sunglasses, but just enough pressure so that you can secure it but not exceed forces and break it maybe. What you have done there, what your brain has done there is to combine efficiently different senses and upon them make actions to perform an everyday task. To your disappointment, my disappointment, this is a really hard task for robotics, and this is what I'm trying to tackle in this PhD. There are two parts in this in my research. The first is sense, and the second is control. Throughout this presentation, I'm going to give you a small introduction about me. I'm going to talk about my research that I've done so far and I'm planning to do that I'm going to revolve around sense and control. I'm going to present my timeline for this research, and I'm going to close with some things beyond the PhD. So, for those who don't know me, I'm Fotios, and this is my first robot that I almost built 16 years ago when I was in a secondary school. Not a great robot, but it was a start. That happened in Thessaloniki, that many of you recently got to explore. That's in Greece, in the south of Europe, and it's in the north part of Greece. Then I went to Technical University of Crete to study electrical and computer engineering. That's in the very south part of Greece, in the city of Chania. The diploma for which I did research for my diploma at the UK, and specifically at Cambridge, and more specifically at the Cambridge Research Lab of Toshiba Research Europe. After which, I got a position as a research assistant at the National Center for Scientific Research Demokritos. And after that, I accepted a position as a graduate teaching assistant at the University of Texas Arlington in the USA. And after that, I started at the team of CPS as a doctoral student and university assistant. To these people, I pretty much know where Austria is and where specifically Leoben is, literally in the center of Europe. That was a brief introduction about me, and let's dive into my research. So as I told you, I'm going to talk to you about sensing and how you use this sensing to control. So let's start with the sense. One part of my research includes representation learning. And what essentially representation learning does is to extract information from raw data. And in my research, I'm using neural networks to do that and different techniques to train them. The other pillar of representation of perception is multimodal fusion, where you need to fuse together different modalities like touch and vision in order for them to work cooperatively. Starting with representation learning, also known as feature learning, the model learns to identify representations from raw data, extracts underlying patterns and correlations, and minimizes the need to extensive human-driven feature engineering. And that improves effectiveness in learned tasks, for example, detection or control in our case. Now for the multimodal of fusion, again, we have everything I would discuss for typical representation learning, but on the top of that, we need to learn presentations that are consistent across all modalities. We need representations that takes into account the specifics of its modality, like its sparsity, its temporality, or its locality, and does not collapse into one or the other modalities, and it pays attention to all of them. But how we do representation learning? What is the best method to do that? Well, for me, it's self-supervised learning. And what is self-supervised learning? Self-supervised learning is supervised learning, but with using data's inherent structure or properties as its labels. And how can that be done? It can be done by predicting missing information. Like you have a stream of data, you remove a part of it, and then you try to predict it. You already have what it should be, and then you try like that. That's called patching. That's called patching. You can compress data. You can squeeze information and try to make it go through there, and in that way, it will figure out how to maintain the best part of the information, the more relevant part of the information. For example, that was the autoencoders, or you can compare positive and negative samples and group them together, which is contrastive learning. And why actually use self-supervised representation learning? Well, because it utilizes abundant and unlabeled data, and you don't need any data annotation, which is very expensive and human intensive. It enhances the model robustness and generalization to new tasks. Yeah, that was not a smooth transition, but yeah. Let's start with the first part of my research for representation learning, and that was improving an inherent problem in variational autoencoders. The VA's objective is this long and boring equation on the top, which essentially has two parts. The left part, which is the reconstruction error, and the right part, which is the KL divergence between the prior distribution, the posterior distribution, and the prior. To have a visual representation of what an autoencoder looks like, it looks like this. It has an encoder part on the left and a decoder part. And what it essentially tries to do is to squeeze information in the middle, and this is where the representation lies. The problem here is that this KL divergence here tries to make this Q function really close to P, and that's what the KL divergence does. The problem is that there is no limit to how close they will be. So in the extreme cases, and when you use neural networks to represent the encoder and the decoder, it collapses. It collapses to the prior distribution, and it doesn't pay attention to the input X. And this is essentially what I just described. Can we use something to actually solve that? Okay, let's find out. Let's try to split the KL divergence and somehow put a limit to it. Do not try to read this equation. It simplifies down to that the KL divergence is lower bounded by the mutual information between the input and the representation. And as we said, by minimizing the KL divergence, which is essentially the objective of the VAE, you minimize the mutual information. And if it goes to zero, you don't have any information going from your input to your representation. And how we can solve that? Well, it would be nice to have a lower bound to the mutual information so it cannot go to zero. So we're certain that there's enough information in this representation. And to do that, we can use the info and C loss. Minimizing it, it will increase the lower bound to the mutual information. And to do that, we use this, formula, which is the info and C loss. But why the info and C loss? I mean, what does it come from? How can we use it in the variational autoencoders? Let's take a step back and let me introduce to you contrastive learning. Contrastive learning, what it does is to take two similar images, like the ones on the left, and make them similar, and take two dissimilar images, like the ones on the right, and make them dissimilar. And the way to do that is the info and C loss, where the info and C loss denominator makes things similar, so the things on the left, and the rest of the things dissimilar, the denominator. And that's the solution that we proposed, called contrastive regularized variational autoencoder, where we just augment the original loss of the VAE with the info and C loss. And this is a work that we presented at ACIAIT. in November of 2023. Okay, moving forward, we have to think, are my priors good enough? This prior distribution that we're trying to match, is it good enough? And as you may remember, this objective of variational autoencoders from previous slides. And this is what we actually did from the decomposition of the KL divergence into mutual information and another KL divergence. And the thing is, can we do more? Can we actually have better representations by manipulating this equation? And to ask this question, apparently it's a yes answer. So we can further decompose the KL divergence into an entropy and a cross-entropy term. And what it gives us is, as I said, the entropy term that gives us randomness within the model's latent distribution, and a cross-entropy term that gives us alignment with the prior distribution. This provides enhanced control, or hopefully will provide enhanced control because it's a working process. It will independently adjust entropy and cross-entropy, give us precise control and deeper understanding of latent variable interactions. And most importantly, it will give us access to more flexible prior, and we would be able to use complex or non-standard priors, and also integrate a domain-specific models if we have it. Pivoting to multimodal fusion, how can we solve this problem? Any answer? Well, it's again self-supervised learning. And known aspect here is contrastive learning. And in this work that we did collaboratively with Vedant, we combined vision and touch with SSL in a model called MVTAC. Essentially, how we train this model is to get two different inputs, get two different augmentations of the same input sample, pass them through the encoders, get the representation, and then create different loss functions. We have intermodality loss functions that pay attention within the same modality, so touch to touch and vision to vision, and intramodality losses that pay attention between the two modalities, that is vision to touch and touch to vision. And altogether, they compose the total loss of our model, MVTAC. And this is the work we presented last month in ICRA at Yokohama. The findings and the results of this work was on two datasets. We trained this model on two different datasets. One is material property identification. With the blue, it's our method, and with green, it's actually the supervised method. And it's important to compare against it because this method creates representations that are specific to the task, whereas the rest of the methods are self-supervised and they're agnostic to the task that we test them on. As we see, our method not only outperforms the rest of the state of the art, but in many cases, it also outperforms the supervised method. Another dataset that we tested on is the grasp success prediction, where we outperformed other state-of-the-art methods there, but we didn't manage to outperform the supervised method. The reason for that being that the dataset was really small and not diverse enough for this method to capture all the variation within the data. That was pretty much the part of the sense. Now that we have methods, or will develop methods to acquire these representations, how are we going to use them to control a robot? Well, there are two ways to go with that. There's reinforcement learning and real-world learning. Starting with reinforcement learning, how we do it. We can do Visuotactile model-free reinforcement learning, and we can also do hybrid model-free and model-based reinforcement learning. Starting with the Visuotactile model-free reinforcement learning, we presented a work where we utilized the work of MVTAC, these representations. We got the same loss function as we got for MVTAC, and we augmented with this one the loss signal coming from different reinforcement learning algorithms like soft-actor critic or PPL. And the result was the M2-curl loss. M2-curl loss stands for multimodal contrastive unsupervised reinforcement learning. And this is a work that I'm going to present next week in Ubiquitous Robotics conference. And last minute, like yesterday, I found out that it's an award finalist. The results of this work, here we have a cumulative reward. So less here is more, because it was a very sparse reward when you achieved the task, and everything else was like for every time you got -1. That's why you have negative rewards. Again, with blue, it's our method, and with green is the ideal method, where it's the methods that had access to the state of the robot. The rest of the methods had access to the observation of the environment through the cameras or the tactile sensors, and had to infer this state. Our method outperforms all of the other baseline methods, and on the top of that, many times it also outperforms the methods having access to the state. And this is a video of such a task where the robot has to push an object through a random trajectory. On the right, you see the tactile sensing feedback, and on the left, what the robot sees. Regarding the hybrid model-free and model-based reinforcement learning algorithms, that's a work that is consequent to this one. We have two different approaches. The objective here is to combine the strengths of both of them. Model-free reinforcement learning, learns from interaction with the environment. It's sample inefficient, but it's fast and it's robust. On the other side, we have model-based reinforcement learning, which learns world models and plans actions according to them. But even though it's more sample efficient, usually the model has inaccuracies, and these inaccuracies accumulate errors in predictions. A hybrid methodology would interplay between these two policies, and when world model has high uncertainty, the model-free policy will take over, and vice versa. A crucial point here would be to align these two policies so that the distributions are close and there's no discrepancy between changing from one to the other. Pivoting to the last part of my research, and that includes the real-world learning, how we do that? Not self-supervised learning this time. We use Visuotactile, sim-to-real transfer, and imitation learning for this one. Imitation learning will consist of many things. That will consist of a data collection scheme, a behavior cloning method to quickly try to train on this model and clone behaviors of experts. And then the last part will be offline reinforcement learning, where you don't need experts for that. Sim-to-real strategies will be focused on Visuotactile data, and it's going to be a continuation of the M2Curl project. And its goal is to bridge the gap between simulated and real-world environments for Visuotactile data. The challenges here are that simulated environments often fail to capture the complexity of real-world tactile sensors. Give me a second. Yeah. Well, not always, not often, but almost always. The reason being that you can observe on your own that they have nothing to do, the simulated with the real-world data. Real-world deployment will have performance discrepancies between simulated training and real-world application. And this research approach to close this gap is domain adaptation. How? Self-supervised learning. And more importantly, train encoder models to represent the same way simulated and real data. If you imagine of an apple, it doesn't have to be a real apple, or you will recognize if it's an apple from the food market or if it's an apple in a kid's cartoon. It's still an apple, but it has different textures, it has different shapes, colors. So yeah. And because they're not good simulation yet, especially for tactile sensing, the last part that's going to focus on imitation learning, its objective is to develop robust models for robotic manipulation. That includes imitation learning and leveraging big data sets, public and collected here in our lab, to fine-tune for all specific setups. The challenges here is that the data sets are It's really hard to set up robots and build ones that we need, like the lip hand. Such setup, you can see it here. Actually, we could do a small break and change from one screen to the other to show you the robot moving. So you can see everything that the robot sees right now. You have the camera feedback, and then you have... Yeah, no, I couldn't do that. And you see that there are like patterns that the camera cannot see on the object and are critical for grasping or any kind of manipulation, but they're visible in the tactile sensing. There are two tactile sensors integrated on the gripper of the robot. Moving forward with the presentation, I want to develop behavioral cloning and foundational model fine-tuning for these data sets. And there, the problems are that we need for behavioral cloning, we need high quality and expert data, because literally you need to copy a good policy, but that lacks of adaptability. It only mimics observed behaviors, and it's limited to, it cannot adapt to new and unseen situations. It fails to optimize also for longer term outcomes. And this is where offline reinforcement learning comes into rescue. Data quality and diversity are also important here, but you don't need data from experts. You have limited exploration, but there are many techniques that can solve that. And again, your policy needs to be adapted on the real robot after training on the offline data set. The timeline for everything I presented to you today is this. I started the first year I worked on CRVAE, and I published the paper on the first quarter of 2023. Then I continued work with MVTAG with Vedant, and that finished with a milestone at the end of the final quarter of 2023. Work package 1 will end, hopefully, by the end of 2024 with the entropy decomposed variational autoencoder. I've already sent a draft of this paper to ICML workshop, to an ICML workshop where it got rejected, but I got valuable feedback to continue this work. For work package 2, sample efficient and robust reinforcement learning algorithms and sim-to-real transfer, we already published a paper, M2curl, and this will continue with Visuotactile sim-to-real transfer. And the goal for that is to submit a paper at the end of 2024. After that, we'll focus my efforts on hybrid model-based and model-free reinforcement learning, probably on the same setup, the same simulator, and then we'll try to also do sim-to-real transfer after that. And that will conclude at the last quarter of 2025. Last work package is imitation learning. That has started a few months ago with the setup of robots and simulators with the help of Nico. And that includes data collection and behavior cloning. The goal here is to submit a paper in the first quarter of 2025. And after that, continue with Visuotactile offline reinforcement learning, which I want to compare against the behavior cloning methods. And that will conclude my PhD at the first quarter 2026. A few things beyond the PhD. I had the honor to supervise 2 master students. One is Melanie, the other is Zin. 2 of them, we were lucky enough to have them in our team as PhD students later on. For a year, I ran the Neural Coffee reading group. I'm writing articles on Medium about almost everything, research articles, and even how to fix common problems with video drivers. I give lectures as part of different classes here at the university that you can find online on YouTube. And my favorite one, the Christmas videos I would do almost every year. That was all. Thank you so much. If you have any questions, I would be more than happy to answer them.